Welcome back. As I mentioned in the previous video when I was talking about the phase diagram of water, that there is a alternate way of showcasing the same concept of phase diagram of water, and that is nothing but the heating curve of water. So what is it? Heating curve. Okay, and that's what you see here, right? Now, in contrary to what we saw in the phase diagram, which is very simplistic view of the various phases of water, here we have a much more complex view. Now, on the bottom, we have heat added, that is, whether you're heating it using a flame or just the heat from your palm or heat from the room, whatever be the source of heat, it's heat added, and it's normally heat in chemistry is measured in kilojoules over mole. That's the unit for the heat. And on the y-axis, we have temperature, right? Now, it only makes sense, right? If you have to go from ice to, like you see in the kettle right here, that steam is coming out, right? So if that's the case, obviously heat has been added, right? So when I said that 0 degree is such a classic point, is that water exists as both solid and liquid. It's just that fine line where they both exist in this, which is this phase right here, you see? Okay, so you start off with ice at say minus 25 degrees Celsius, and then you continue to supply heat until you get to 0 degrees, right? Where the water is still in the ice phase, but you want to understand something when you read graph is, when you see something is going up or down, it is changing. When you see a flat line, means temperature is constant in this region of 0. So maybe until you hit maybe 8 degrees, I'm just making this up because this is 10, so 8 degrees. Water is still in the ice and it's trying to get into the liquid phase. Right when it hits, say, this 8 degree mark, it's now in the liquid state, right? Now again, here you're continuing to add heat again and again and again until you hit 100 degrees. So this is when water boils, right? And then, so you're no longer in the liquid phase. Right now, liquid and gas are in a combined form. If you try to heat water in a beaker or something where you can actually see, you see droplets of water on the sides of the wall, right? That is this phase right here, okay, where liquid and gas are existing in a dynamic equilibrium, okay? That is, whatever is liquid is becoming gas, and whatever is gas is coming back to liquid. Now, as I've already said to you, liquid to gas is evaporation, and gas to liquid is condensation. This dynamic equilibrium exists in this region. So, which means at 100 degrees, you're adding, I should have said 8 kilojoules, sorry. It's not degrees, it's kilojoules. So, maybe at 8 kilojoules, you had just reached water. And so right around 15 kilojoules is when you have achieved that liquid vapor dynamic equilibrium. And between 15, you see, you needed almost 55 kilojoules per mole, right? And this is right the point where, you know, after this point, it's purely just gas, right? Or steam if you're heating water. If you're heating some other liquid, you may not always get steam. It's just pure gas, right? So we have continued to add from when you add heat, right? It's positive. When you give out heat, it's negative. But in this case, if you have to go from water that's at minus 25 degrees all the way to, say, 125 degrees, which is where this graph ends. So you've gone from minus 25 degrees to 125 degrees. That's huge. That means you have put in a lot of heat from various sources. I guess with ice, you know, just a palm heat would be enough, but if you're at minus 25 degrees, maybe your palm is not the best source of heat. It's probably actually a real heat of whatsoever. Now, let me bring up one of the conceptual questions I posted earlier, right? Which is, why is it not recommended to consume snow when you're caught up in a blizzard, right? This is the graph that will help you answer that question. Now, I'm not going to give you the answer even at this point, okay? I still want you to figure out. Say, we are assuming that the snow is at 0 degrees. The snow could be at even minus 25, minus 60, but say the snow is at 0 degrees, right? And if you are at that temperature, your body is getting close to that. Your body is at 37 degrees Celsius internally, right? Which is right around here, right? I'm trying to help you understand the question better, right? So your snow is at 0 degrees or even lower, but your body is at 37 degrees Celsius. Now, using this graph, okay, why do you think it's not recommended to consume snow when you're stranded in a blizzard? Maybe ultimately I will give you the answer, but I want you to still think about it, right? So this region right here, I'm going to get a different color, okay? I'm going to overlap this. When you are going from this ice, which is a solid, to ice, which is a liquid, shouldn't say ice, but liquid ice, which is cold water, which is this region, this is called enthalpy of fusion. Remember what I said about enthalpy? Enthalpy is nothing but heat change, right? So what do you think could be the enthalpy? So this would be around, say, 2 kilojoules per mole, okay? And to go from here to here, it's a flat line, means temperature remains constant, but heat is being continued added, right? So what is the enthalpy of fusion? Again, these numbers are very arbitrary based on the numbers I've given you. So enthalpy of fusion would be 8 minus 2, which is 6 kilojoules per mole. Fusion is when you go from solid to liquid, that is ice to cold water. Now, this region right here, okay, this is when you're trying to go from boiling water to gaseous or steam, right? Like it's shown in the kettle here. This region is called enthalpy of vaporization. What is enthalpy of vaporization? Well, I already told you this is around 55 and this is 15 and 55. So enthalpy of vaporization is 55 minus 15 kilojoules per mole, which is about 40 kilojoules per mole. So let me bring back the conceptual question one last time. Why is it not recommended to consume snow when you're stranded in a blizzard? Say your body temperature, maybe depending on how long have you been in the blizzard. Say if you just got caught up in the blizzard, your body temperature is internally 37 degrees. But what if you're stranded there for a lot longer? Then your body temperature is already lower, say at 25 degrees Celsius. So you can assume as many situations as you want to help you answer that conceptual question. But the take-home message from this is enthalpy of fusion, which is solid going to liquid, that is melting of solid. Enthalpy of vaporization is going from liquid, boiling liquid to gas, or in other words, liquid to gas, right? Now, if you also notice on the top, these are water molecules. When it's ice, molecules are tightly packed, right? We all know that gases occupy the best shape of the container, and then liquid, and then solid. That's because solid molecules are tightly packed. As ice begins to melt, and then you see that some molecules are intact. This is what I call the slurry, which is right around here. You see, it's 6 kilojoules per mole, right? And I arbitrarily matched it, it's 6, right? So reading a graph is such an important aspect of being in a science classroom. So how to read a graph, what is increasing, what is decreasing, when is something constant, is all important. You see, this is a slurry where you have some, you know, you all heard of sleet, right? That's kind of what it is on a road. You have some ice, some water, but it's still not purely liquid or solid. It's that state, which is this constant line. And then you go from liquid, water, warming. This is important for answering the conceptual question. If you're looking for an answer on why you should consume snow, this is where your answer is really reminding. So liquid, water, warming, maybe a little bit up till here. Okay. I'm not asking you to just know all this and memorize it. Okay. This is conceptually understanding it. And to go from actual liquid to gas, I said about 40, and that answer matches this. So this is this region right here, this flat region. And then obviously above this, you only need a little bit more. Once you attain this point, then you just need just a little bit more energy to go into pure steam, right? And then this is where the answer to the second conceptual question remains, which is, why is boiling water less hazardous, relatively less hazardous if it falls on your skin over steam? Think about it, because this is where water is boiling. This is where steam is existing. So if you put this on your skin versus this, what do you think is causing the burn to be more serious with the steam over a boiling point? But the take-home message also from this graph is enthalpy of fusion is solid to liquid, enthalpy of vaporization is liquid to gas. Okay, remember these two terms because we're going to do a couple of problems, and then so I want you to be familiar with it. And then, like I said, standard temperature and pressure is 1 atmosphere and 273 Kelvin or 0 degree Celsius. Remember these terms because I don't want to keep repeating it in all my videos. All right, so stay tuned for more videos.